All right, let's go ahead and get started with question number 1 on the circular motion and rotation practice problems solutions. Here we have a diagram that shows the top view of a student at point A on an amusement park ride. It spins the student in a horizontal circle of radius 2.5 meters at a constant speed. The floor is lowered and the student remains against the wall without falling to the floor. Part A, draw the vector for the centripetal acceleration for this diagram. Now, the centripetal acceleration is the tangential velocity squared divided by the radius, and it is always pointing inward. So our vector, the blue arrow, shows this inward vector for the centripetal acceleration. Part B, which direction is force normal? Force normal is always perpendicular to the surface. So in this case here, the student has his or her back against the wall. Therefore, force normal is perpendicular. Force normal is our centripetal force in this problem as indicated by the red vector. Lastly, which direction is the force of friction on the student's body? Friction is opposing the direction of motion. This student's body is not falling down to the floor. Force of friction is actually up the wall of the ride, and so that's actually coming out of the screen at you up the wall. So question 2. Which graph best represents the relationship between the magnitude of the centripetal acceleration and the speed of an object? Okay, so we have a constant radius here, and you're being asked to choose, as we've been doing throughout this course. You're looking at something tangential, centripetal acceleration, in which you have the tangential velocity squared divided by the radius, and you're comparing it to the speed, so the magnitude of the velocity. That's what we're looking at here. We have, you can see that the speed is directly proportional to the tangential velocity squared. So we have a relationship in which one variable is proportional to the square of another one. So we're going to be looking for a graph that has some curvature. Also, that leaves us with 2 and 3. Also, we know that they are directly proportional, not inversely proportional. Therefore, our best choice here is going to be graph number 2 here, which is showing this exact relationship. In question 3, a 0.5 kilogram object moves in a horizontal circular path with a radius of 0.25 meters. Let's take a look at the schematic diagram. As I've shown you in class, the horizontal circular path, that's very similar to what you're doing in AP Lab 8, where you have it above your head, swirling it, as opposed to a vertical circle where you would have it out in front of you. So here we have a radius 0.25 meters, speed 4 meters per second. That would be the magnitude of the velocity. And you are being asked, what is the magnitude of the object's acceleration? So in order to find this, we're going to use our formula for centripetal acceleration being the tangential velocity divided by the radius. You have the velocity. If you square it and divide it by 0.25 meters, you end up with 64 meters per second as the magnitude of the centripetal acceleration. And of course, the direction of the centripetal acceleration is going to be inward. All right, and here, as I've always done, a further affirmation, you can look at your units and confirm that they end up working out with meters per second. In question 4, an object of mass 5 kilograms is moving in a constant speed of 6 meters per second in a circular path radius 2 meters. Find the object's acceleration and the net force responsible for this motion. So, drawing a schematic diagram here, we show our radius of curvature, our velocity at a given point, and the mass. If we go ahead and first solve for the centripetal acceleration, again, that's velocity squared divided by radius. We have velocity, we have a radius, so that is 18 meters per second inward. And to find our forces, we're going to sum our forces centripetally. These are our inward forces. And in this case here, we have that the forces are equal to, and the mass multiplied by the centripetal acceleration. And so really that's all we need to find the net force, because there is only one inward force in this particular problem. So mass times acceleration, and again, this is centripetal acceleration solved in part 1, gives us a centripetal force of 90 newtons inward. Okay, so just a reminder from some of the facts on the problem set that forces that are centripetal, you will always label on a free body diagram as the true force they are. Force centripetal is not a new force. So all of the forces that we've learned about in our study of dynamics can be center-seeking or centripetal forces. Example, force of gravity, force of friction, force of tension, and force applied. Okay, so those are some examples of centripetal or inward forces. Again, force centripetal is not a new force. Question 5, we have a 10 kilogram mass. It's on a string with a breaking strength of 200 newtons. If the mass is whirled in a horizontal circle of radius 80 centimeters, what is the maximum speed that it can have? So again, an analysis here. We show the horizontal circle. We have an inward force. That would be the force of tension. And if we sum in the vertical direction, we have the force of gravity also acting on this object. So let's go ahead and sum the forces inward. The forces inward, the sum of those forces would be the force of tension. There are no other inward forces. Therefore, force of tension equals mass times the centripetal acceleration. We have our formula set up. We are asked for the maximum speed. We've converted 80 centimeters into base SI units of 0.8 meters. We have velocity squared in the numerator. The square root, therefore, would give us a maximum velocity of 4 meters per second inward. Okay, so that would be our maximum speed that we can have. And of course, this object is constantly changing direction as it is manipulated into a circle. And at any given point, if we were to exceed this maximum speed, the string would break and the object would fly off at a tangent to the circular path. Here is a beautiful picture that my daughter decided to draw while I was making these solutions. This is a picture of herself, and I thought I would share it with you guys. Moving on to question 6, an athlete who weighs 80 newtons, so that is the weight, mass times the acceleration due to gravity, is running around a curve at a speed of 5 meters per second in an arc with radius of curvature, 5 meters. Find the centripetal force acting on him. What provides the centripetal force? What could happen to him if R were smaller? Okay, so here we have a guy running around the path, And the centripetal force is the inward force, the center-seeking force. It is always positive, and it is always labeled as the actual force it is. And in this case here, it's the force of static friction that is providing the centripetal force. Okay, so the force of static friction is equal to mass times centripetal acceleration. We have all of this information, so we can solve for the force centripetal, which is the force of static friction, to be 400 newtons inward. Okay, so here we can look at the fact if we're asked to compare what would happen if R were smaller. Let's look at this through a semi-quantitative perspective using some mathematical reasoning. Force centripetal is proportional to the inverse of the radius. So as the radius increases, force centripetal decreases. If the radius decreases, which we're asked specifically in this problem, if R were smaller, if the radius gets smaller, the force centripetal gets larger. Again, mathematically, we're showing here through the fact that it's an inverse relationship, that as force of static friction goes up, that force of static friction goes up as a result of the radius going down. So if we exceed the force of static friction maximum, we have slippage. In other words, this individual would go off at a tangent to the radius of curvature. Okay, and of course, if that were to happen, force of static friction would become force of kinetic friction. Question 7 here, you're given a diagram on the problem set. We have a vehicle traveling at a constant speed. It follows a horizontal circular path. You're given the radius of curvature, and you're asked specifically what would happen at point P. So at point P, there's a patch of ice. In other words, mu equals 0. So the coefficient of kinetic friction is 0. All frictional forces are lost between the tires and the surface. So A, which path does the car follow on the ice? All right, so if we look at our forces occurring here, we have forces in the vertical direction, which would be force normal minus the force of gravity. The vehicle is not accelerating vertically. There's no net force vertically. Therefore, we have force normal is equal in magnitude, opposite in direction to the force of gravity. All right, so for part A, if the vehicle hits a patch of ice, we're going to have that it will follow path B. See how that path B is going to be at a tangent to the radius of curvature. So it would follow path B in that case if we lost the center-seeking or centripetal force. Part B, what was the magnitude of the centripetal force the instant before it hit the ice? Well, we have the information to sum the forces inward, being the force of friction. We have mass, tangential velocity, radius of curvature. So that would be 3,888 newtons inward. Part C, what is the coefficient of static friction for the car's tires, okay, before hitting P? Because we know what happens when the vehicle hits point P. We lose our centripetal force. Friction equals 0, okay? So before P, we're asked about mu, so we're going to be using physics as fun, and recall that mu is equal to the force of friction, in this case static friction, divided by force normal. That means through our vertical summation, we can take our recently calculated force of static friction, because that was the centripetal force here that we found in part B. And we can take the fact that we know from our vertical summation here that the force normal is equal in magnitude to mass multiplied by the acceleration due to gravity. So we take our 1,200 kilogram car and multiply that by the acceleration due to gravity, or 10 meters per second per second. And we get a mu value of 0.324. Question 8. The maximum speed with which a 945 kilogram car can make a 180-degree turn is 10 meters per second. The radius of the circle through which the car is turning is 25 meters. Calculate the force of friction and the coefficient of friction acting upon the car. So this would be the force of static friction here. The vehicle is making this turn, this 180-degree turn. So this schematic helps to clarify what's going on. We're given the speed at that instant. Again, to reiterate, if we lose the centripetal force, the car goes off at a tangent to the radius of curvature. We're given the mass. And so what we can do now is calculate the force of friction by summing our forces inward, or centripetally, being the force of static friction is equal to the mass multiplied by the centripetal acceleration. We have all the information we need to calculate force centripetal to be 3.78 times 10 to the third newtons inward. In the second part of this question, we're asked about the force of friction, which is force centripetal, so that would be the same. And lastly, we're asked to calculate mu. Well, we know the force of friction, and we're going to divide that by force normal. And here we have a 945 kilogram vehicle, and from our summation vertically, we know that the force normal is equal in magnitude, opposite in direction to the weight, or the force of gravity acting on this vehicle. So we're simply going to take the mass of the car and multiply it by 10. Students often forget to do that. Then we have force normal, and we're going to put that into our equation, solve for mu to be 0.4, and remember, mu is dimensionless. In question 9, Sophia makes 38 complete revolutions on a playground merry-go-round in 30 seconds. If the radius of the merry-go-round is a meter and her mass is 16 kilograms, determine the period of motion, the frequency of motion, and the speed at which she revolves, and lastly, the centripetal force. Okay, so recall from your facts on the problem set that the period is the amount of time in seconds to complete one cycle. In this case here, this would be one revolution, or the circumference of the circle, or 2 pi r. So we're told in this problem it takes her 30 seconds to complete 38 revolutions. Therefore, her period would be 0.79 seconds. That is the amount of time it takes Sophia to complete one revolution or cycle. Okay, in part B, the frequency of motion. The frequency is simply the inverse of the period. Now I have just this little button here can be used, and we'll use this later on in the course as well. On your calculator, that's a very convenient way to find the inverse of a number. So in this case here, 1 divided by the period gives us 1.26 hertz, which is a derived unit, base SI. Recall, hertz would be the inverse of a second. Okay. Part C, the speed at which she revolves. Well, we know the radius, we know the amount of time, we know, the amount of time, the period for one revolution. One revolution is the circumference of the merry-go-round, which is equal to 2 multiplied by pi multiplied by the radius, and we know the radius. So she completes 1 revolution, or 2 pi r, in 0.79 seconds. What is speed? Speed is the the change in position over the change in time, distance divided by time. And we have everything we need to solve. In this case here, we can find her speed to be 7.95 meters per second. She's really moving quite fast here. And D, the centripetal force. Okay, so what is the centripetal force? Well, the centripetal force is the force of static friction. And we can calculate that now because we've found her tangential velocity, or the magnitude of her tangential velocity, to be 7.95. If we square that, divide it by the radius of 1 meter, and multiply that quantity by her mass, we can get the centripetal force, which is the force of friction, being equal to 1,011 newtons. Wow. Okay, question 10. A roller coaster enters a circular loop portion of a ride. At the very top of the circle, the speed of the car is 15 meters per second, acceleration downward, okay, which is pointing in the direction of the center of the circular path, and thus would be the circular force. If the diameter is 40 meters, okay, I'm going to go ahead and underline that. Diameter, we want the radius. We're going to divide that by 2. And the total mass of the car is 1,200 kilograms. Find the magnitude of force normal exerted on the track. Would the person in the car feel lighter or heavier? So what would be the apparent weight of an individual in the car at the top of this loop on a roller coaster? Let us sum the forces here. And foremost, please note, we have 2 inward forces. We have force normal pointing inward, but we also have the force of gravity, which is directed down and toward the earth. And it is also going to be our centripetal force. So when we sum our forces inward, we're going to have two positive forces, because centripetal forces are always positive. Notice on the free body diagram how I've labeled them as the actual force they are, because force centripetal is not a new force. So the existing centripetal forces are force normal plus the force of gravity, or mass multiplied by the acceleration due to gravity, being equal to mass multiplied by the centripetal acceleration. So if we put in values and we also factor out mass, I'm doing this for a reason. If I factor the mass out of this expression, it becomes quite evident that I am subtracting the acceleration due to gravity from the centripetal acceleration. Again, I'm subtracting the acceleration due to gravity from centripetal acceleration. So we get a force normal of 1,500 newtons. So force normal in this case is less than the force of gravity. Force of gravity being 1,200 kilograms multiplied by 10. All right, so we're showing here that an individual's apparent weight would be less than normal. All right, the individual feels lighter. All right, so now in question 11, we're going back to question 10, but this time we're analyzing the scenario when the car is at the bottom of the loop. Again, we're going to use a semi-quantitative perspective here. So if we draw a schematic and write down everything we know, this time we're at the bottom of the loop. If we sum our forces for this scenario, we see there's only one inward force, that would be force normal, and the force of gravity is directed down toward Earth, whereas force normal in this instance is directed up, and that is toward the center of our circular path, and thus force normal is our centripetal or inward force. So when we sum the forces inward or centripetally, we get force normal minus the force of gravity equals mass times the acceleration centripetal. When we solve for force normal in this case as compared or in contrast to question 10, and we factor out mass, we see that we're adding the acceleration due to gravity here. So we would expect an individual's apparent weight at the bottom of the loop to be much greater because force normal at the bottom of a loop is much greater. Again, we're showing this semi-quantitatively in both questions 10 and 11 by analyzing the scenario at the top and or bottom, by summing the forces and factoring out mass to really show whether we're adding or subtracting the acceleration due to gravity, little g. In question 12 here, Sophia experiences a downward acceleration at the top of a loop and an upward acceleration at the bottom of a loop. We're using Newton's second law to determine force normal acting upon Sophia's roller coaster car for both of these scenarios. For scenario 1, we'll draw our free body diagram and label our forces, force normal and the force of gravity. We're going to sum the forces centripetally. So here we're going to have our one center-seeking force being the force of gravity, and we're going to subtract force normal and equal to mass times the centripetal acceleration here. So we can, again, factor out mass to show that we're adding here the acceleration due to gravity, which we are given here, and we can solve force normal being equal to 31,363 newtons, okay? So in this scenario here, we have one center-seeking force that is force normal. Force normal is up, which is in the direction of our center-seeking force, or excuse me, which is in the direction of the center of our circular path, and we're subtracting the force of gravity, and in this case here, we get a value for force normal. Now, go ahead and make a prediction as to what the value for force normal, relatively speaking, would be for Sophia's car when it is at the top of the loop. In this instance here, our free body diagram shows that when the car is at the top of the loop, there are two centripetal forces or inward forces directed toward the center of the circular path. Those would be force normal and the force of gravity. We've shown in previous problems that the force of gravity is going to be greater in magnitude than force normal. Now we can sum our forces for this scenario at the top of a loop. We can even factor out mass yet again and show we are subtracting the acceleration due to gravity. And so by subbing in our centripetal acceleration and solving, we can get force normal to be equal to 4,838 newtons. Now compare these values, bottom of a loop, top of a loop. This further supports what we've been looking at in the last couple problems. Question 13, we get into a derivation. We have a rock, mass m, on a string. It is being spun in a vertical circus, so a vertical circle of radius r at a constant speed. All right, so we have a constant speed. At the top of the circle, the tension is twice the weight of the rock, okay? Twice the weight of the rock. Derive expressions for the following. Before we derive, let's analyze what we've been told here. So we have a rock, and it's in a vertical circle, and we're being told that the force of tension is twice the weight. So we have our radius, we have our mass, and we were told explicitly that our derivations will be in terms of m, r, and any other fundamental constants. Well, for part A, we're explicitly told this. So the force of tension, capital T, is equal to twice the weight. What is the weight? Force of gravity. Mass times the acceleration due to gravity. Therefore, for part A, force of tension is simply 2 mg. Okay? G is one of our fundamental constants that were being used in our derivation here. Part B, the speed of the rock at the top. Okay, well, in part B, at the top of the loop, if we were to draw a free body diagram at the top of the loop, there are two center-seeking forces. There's the force of tension and the force of gravity. So by summing our inward forces, we have force of tension plus force of gravity. However, we've derived force of tension to be 2 mg, and we know the force of gravity is mg. So we're going to set those equal to mass times tangential velocity squared divided by radius. We're then going to add and simplify this, and remember, for this particular question, we're being asked for the speed at the top. So let's multiply both sides by the radius, and let's take the square root of that quantity and solve for our speed to be equal to the square root of 3 times the acceleration due to gravity times r. And that is our answer for part B. For part C, we want the speed at the bottom. Well, I've underlined in this problem we're at a constant speed. Therefore, the speed at the bottom is the same as the speed at the top, which we derived in part B to be equal to the square root of 3gr. Finally, in D, the tension of the string at the bottom of the loop. Well, we're going to need to then sum our forces then at the bottom of the loop, in which case we have the force of tension directed inwards, so that will be our centripetal force, which is always positive. Force of gravity directed downward toward Earth, so we're going to be subtracting the force of gravity from the force of tension. We derived the force of tension earlier, but now we're asked to derive it at the bottom of the circle. And we've learned through several problems now that the force of tension at the bottom is going to be greater than the force of tension at the top, and we've shown that semi-quantitatively repeatedly here in the last few questions. So let's go ahead and put in what we know. We know that we're subtracting the force of gravity mg, so we can set the force of tension capital T, and by adding the force of gravity to both sides and factoring out the mass, we end with this expression where we have the mass multiplied by the quantity of the tangential velocity squared divided by r plus the acceleration due to gravity. We know the velocity is constant, so let's go ahead and plug in our previously derived expression of the square root of 3gr. Let's go ahead and plug that in for the velocity. We're squaring it, so now we simply have the quantity 3gr divided by the radius plus the acceleration due to gravity. Therefore, we can simplify this expression and solve for the tension at the bottom of the loop, and we get that the tension at the bottom of the loop is 4 mg. In fact, it's twice the magnitude of the tension at the top of the loop, which makes sense from our earlier intuition and from questions 10, 11, and 12 when we analyzed roller coasters. All right, number 14 here we have an experiment. This is the exact experiment that you did in part 1 of AP Lab number 8. And so we have a rubber stopper and we're twirling it around and we're asked a couple questions here. Part A, Describe what would happen to the radius of the circle if the student whirls the stopper at a greater speed without changing the balancing weights. Now remember, those balancing weights are the weights that are supplying the theoretical force of tension, which is our force centripetal for this scenario, because it's the rope, the string, and the masses that are hanging from them that are the centripetal force. So in this lab, hopefully you've already had an opportunity to explore this because it's fairly intuitive. If you were to begin to whirl at a greater tangential speed, what's going to happen is your radius is going to increase. And as always, we can look at this from a mathematical reasoning or a semi-quantitative standpoint or perspective. We would show that if this is the same, okay, oops, let me go back. If this is the same, because we're not changing the balancing weights, and this went up, the radius would also increase. Again, force of tension is the same. Mass is obviously the same. The tangential velocity increases, therefore the radius must also increase if force of tension is to remain constant. All right, so let's go ahead and look at part B, where you're asked to draw free body diagrams for the scenario here, where we have our force centripetal being our force inward. In this case here, in contrast to the horizontal, now we're looking at a vertical circle. So we show here force of tension is our inward or positive force. We subtract force of gravity, which is downward and directed toward Earth, and we set that equal to mass times the centripetal acceleration. Okay, so as we've shown repeatedly, which means this is very important, when we factor out the mass at the bottom of this loop vertical circle, we're going to be adding the acceleration due to gravity. So we're showing force of tension is going to be much greater, as we've shown in our derivation in question 13, than it would be at the top of a vertical circle. All right, question 15. Amadeo drives his car clockwise around a circular track. We're given the radius. Amadeo completes 10 laps around the track in 2 minutes. Find Amadeo's total distance, average speed, centripetal acceleration, and we're going to compare that to Amadeo's displacement and average velocity. So let's look at what we know here. We know that 1 lap around the track is equal to 1 revolution, is equal to the circumference of the circle, is equal to 2 pi r. So we can find the distance or the magnitude of the displacement by simply multiplying 10 times 2 times pi times the radius, and we get 1,885 meters for the distance. We're also asked about the speed. Well, speed is distance divided by time. We've calculated the distance. We know the time. We're going to convert 2 minutes into seconds, base SI units. So we're ensuring we end with meters per second, and the speed that Amadeo has is 15.7 meters per second. What is the centripetal acceleration? Well, that would be the tangential speed squared divided by the radius. We found the speed to be 15.7. We square it, divide by 30 meters. So we get the centripetal acceleration to be 8.2 meters per second inward. In part B, we're asked about the displacement and the velocity. A change in position or displacement is equal to the final position minus the initial position, which is equal to 0. So if the displacement or change in position is 0, then the average of velocity is also going to be 0. 0 divided by the change in time is 0. Therefore, the average velocity is also equal to 0. Question 16, we have a banking problem here. In this problem, banking is what allows vehicles to travel around a curve at or below a posted speed limit. So in this diagram, we have a radius of curvature of 60 meters. The curve is banked at an angle theta, which is equal to 11.8 degrees. What is the ideal speed on this curve for the car such that no friction is needed to provide centripetal force for the car? In other words, at this exact speed, a vehicle could take this turn on a frictionless surface. In other words, like a sheet of pure ice, mu equals 0. But the vehicle must have this exact speed for these exact conditions. So this question is showing how force normal can be, or rather a component of force normal can be our center-seeking force. In an environment in which there was also friction, we would have the force of static friction also being a centripetal or inward force in addition to a component of the force of gravity. So let's go ahead and get to this problem. Analyzing the situation here, I want you to think this vehicle is coming out of the computer screen or your phone, and it's coming at you, okay? In contrast to problems that we've solved in the past where we have objects that are sliding down or up in parallel an incline. This is not sliding up or down the incline. It's coming directly out of the screen, okay? So that's important for you to conceptualize as we go through and analyze these different forces acting on the vehicle. So we have our theta, which we're told about here. We have a free body diagram, and we're showing force normal. Force normal, whether you're using the diagram on the left or right, is always perpendicular to the surface, but the surface is at an inclination. So that means we're going to be resolving force normal into perpendicular and parallel components, or x and y components. So let's look at our theta here. If you play around with the geometry, you can show that this angle theta is equal to this angle theta. Just look at your 90-degree angles there. It's fairly obvious. Good morning, sweetie. Come say good morning to all my students here.
Good morning.
Good morning.
What is that?
That is a microphone.
I call it a microscope.
All right, so what we're going to do now is we're going to do what we always do. We're going to draw free body diagrams, and we're going to sum the forces. This time, we're going to do that for the vertical direction and the inward direction to show that a component of force normal is indeed the centripetal force. Let's start with the vertical summation. Vertically, we have that force normal cosine theta. Let me show you this real quick. So we have our angle theta here, and the vertical component of the resultant vector is cosine. It is adjacent. So our hypotenuse or resultant vector is force normal. The vertical component in this case is force normal multiplied by cosine theta, and opposite of that we have the force of gravity. Summing the forces and calling up positive, we have force normal cosine theta minus force of gravity equals mass times the acceleration vertically. However, the vehicle is not accelerating vertically, therefore that is equal to 0. That allows us to go ahead and isolate force normal, which is a good stopping point for the vertical summation. So if we isolate force normal, we can show that it is equal to the force of gravity divided by cosine theta. Now let's move on and take a look at our inward direction. And the problem clearly states that there is only one centripetal force, which is a component of force normal, because we're talking about this ideal speed in which friction is not needed. Otherwise, as I just explained, there would be force of static friction. There would be a component of that would be inward as well. So, summing the forces inward, we get that the force normal sine theta. Again, if we look at our geometry here, this is that inward force. It is opposite of theta. You can use this triangle as well. Using this angle is equal to 11.8 degrees. Opposite of that, and of course our hypotenuse or resultant vector is force normal. So force normal sine theta equals mass times the centripetal acceleration. Now here's something we've done a lot in the past. We're going to take this, which we isolated from the vertical summation, and we're going to substitute it in for our inward summation. By doing that, we get the expression that the force of gravity divided by cosine theta multiplied by sine theta equals mass times the centripetal acceleration. So let's go ahead and simplify this further by looking at the force of gravity, and we have sine over cosine. That's tangent. So sine theta over cosine theta equals tangent theta, and everybody brought mass, so we can cancel out the masses. Mass does not matter, and so we end up with tangent theta equal to tangential velocity squared divided by radius. Let's multiply both sides by the radius and take the square root to end up showing that the speed is equal to the square root of radius multiplied by the acceleration due to gravity, tangent theta. Finally, we can take our numbers and put them in and solve for the speed to be 11.2 meters per second. That is the ideal speed, and this vehicle could make this turn in a frictionless environment. So the question really says, what is the posted speed limit? Probably not 11.2 meters per second. So converting that into kilometers per hour, we would post about 40 kilometers per hour would be the speed that you would want to hit this curve at to be able to make it around the curvature. So the next question here, we're going to do a bunch of conversions, getting us some practice. We're going to go degrees to radians, radians, degrees, revolutions to radians and degrees. Let's start with 90 degrees, and we have in one circle, in one cycle, there's 2 pi radians, there's 2 pi r's, there's 1 revolution, there's 360 degrees. So we can say, take 2 pi radians divided by 360 degrees is equal to 1.57 radians. Now I should say there are multiple ways you can do these conversions. I'm not going to show them all to you, but if you got 1.57 radians, you're doing this correct. For example, 90 degrees times pi radians divided by 180 will also work in this case. So let's do 6 radians 2 degrees, 6 radians multiplied by 360 degrees, 2 pi radians. So these, again, you're showing, as we've done in the past, we're factor labeling, dimensional analysis, whatever you want to call it. We're using this to factor out and convert from radians to degrees. And 1.5 revolutions, well, 1 revolution is 2 pi radians, is 2 pi r, is the circumference, is, is 360 degrees. So here we're converting 1.5 revolutions multiplied by 2 pi radians is 3 pi radians, or 9.42 radians, and converting 1.5 revolutions into degrees, 360 plus 180, we get 540, 540 degrees for 1.5 revolutions. Okay, so in our next question, we have an insect, and it is at the top of a bike wheel with a diameter of 0.75 meters. That's the diameter. We're going to divide that by 2. Assuming the wheel turns counterclockwise, what is the angular displacement of the insect before it is squashed under the wheel? What arc length does the beetle travel through before it is squashed? All right, so now we're going to take what we did in question 17 and we're going to start applying it, and we're going to start also converting between translational and angular quantities. So on your problem set, you're going to want to have the UCM, uniform circular motion, equations readily available, as well as your conversions between translational and angular quantities. All right, so first part of this, what is the angular displacement? Well, the angular displacement is 180 degrees. You can see that for the insect to go from here to right here is 1/2 of 360 degrees. So we could say that this was equal to pi radians. All right. But the point is just being able to convert between these quantities. Now, for the arc length, we're going to take our degrees, and we can say in 360 degrees, there are 2 pi times a radius, which is equal to the circumference. And because we have the diameter, we can divide that by 2 to get the radius, which converts us now into base SI units. So our arc length is equal to 1.18 meters. Again, you could have just said pi r is equal to 180, and therefore pi multiplied by the radius gives you the same exact answer. You could have also converted this into radians and gone from there. As long as you are getting to an arc length of about 1.2 meters, you're good. All right, so in question 19, we have a bag of sand that is on a merry-go-round. We're given the radius, we're given the mass, and we're told that it's rotating with a constant angular velocity of 6.58 radians per second. We are asked to find the coefficient of static friction between the bag of sand and the merry-go-round. Lastly, you're asked, what do you think will happen to the bag of sand? So I would like to reference the table to help you convert between translational and angular quantities. Remember, to get an angular quantity, all you're doing is taking the translational quantity and dividing that by the radius. So, first question is, what is the centripetal or inward force? In this case, it's the force of static friction. And so we're going to set the force of static friction equal to mass times centripetal acceleration. However, we are given the velocity as an angular quantity, so we're going to need to convert into a tangential or translational quantity. By doing so, we know that we can take the translational quantity and multiply it by the radius, and that's going to give us a linear quantity of 9.87 meters per second. So now we can continue on and find that coefficient of static friction using the physics is fun equation. So putting all of our values in, we are able to solve for the force, and we find the force of static friction to be equal to a little over 1,200 newtons. Using physics is fun, we can go ahead and put in force normal and acknowledge that since the bag is not accelerating vertically, force normal is equal in magnitude to the force of gravity. That's going to help us to solve for mu. Let's take our 18.5 kilogram bag, multiply it by the acceleration due to gravity of 10 meters per second, we get 185 newtons multiplied by mu. Okay, and lastly, we're going to solve for mu by saying we have our just over 1200 Newton force divided by 185 newtons, and that's going to give you a mu value of 6.5. So we're asked, what do you think will happen to the bag of sand? Well, you should immediately say that is a really, really ridiculously high value for mu. We've never talked about a value this high. In fact, rubber on concrete can have a maximum static friction of 4, according to some of the research I have done. So more than likely, this bag of sand is not going to stay on the merry-go-round. In fact, this bag of sand is going to fly off at a tangent, and it will not remain in circular motion. Given this angular velocity, the mass, this isn't going to happen. Okay. In question 20, we have a car's tires, and they are rotating counterclockwise 3.5 times in 0.75 seconds. What is the angular speed of the tire? And then you're asked to convert that into revolutions per minute. As I've said in class, I want to make sure that you are using your calculator correctly and actually dividing by the right quantities. Okay, so let's go ahead and get started with this one. 3.5 times, that means it's 3.5 times 2 pi r, so it's going around in that circumference 3.5 times. So what we can do is multiply 3.5 times 2 times pi radians. And remember that it's that distance around the circle or circumference over divided by the amount of time it takes to complete. So we're told that it's doing 3.5 2 pi radians in less than 1 second. If we divide that, we end up with an answer of 29.3 radians per second. And now we're going to work on converting this into revolutions per minute. Okay, so recall 2 pi radians is 1 revolution, and 1 revolution is in the numerator, and we're trying to get revolution. So now let's go ahead and get our seconds, 60 seconds and 1 minute. That gives us revolutions per minute, and you should get a value of 279.8 revolutions per minute. Many of you, when you plug this in your calculator, you will not get this. Make sure you are dividing by the quantity 2 pi. Question 21 is a classic physics problem in which we have a space station rotating. We're given the angular velocity, and we're told there's a ladder extending from the center of the space station out to the outer edge. Okay, so find the centripetal acceleration at 3 points extending from the middle, okay, all the way out to the outer edge. So let's get started with the middle, all right? Well, centripetal acceleration is tangential velocity divided by radius. So we're going to sub in our angular quantities. So we're given radians per second. So we're going to take the fact that tangential velocity is equal to the angular velocity multiplied by the radius. We're going to square it, divide it by r, which will simplify to omega squared multiplied by r. So this is another way that we can express the centripetal acceleration, except now in terms of angular quantities. So let's go ahead and start with the middle. In the middle, we have our radians squared. However, the distance r in the middle here is 0. So there is 0 centripetal acceleration at this point. Let's move halfway out. Halfway out, we see at 57.5 meters out, or distance from the radius, we have 4.9 meters per second. So that is the centripetal acceleration halfway up the ladder. And let's see what happens if we go all the way to the outer edge. And you might have a clue here what happens by looking at this guy here. Let's check it out. If we go all the way 115 meters out at this exact angular velocity, we end up getting the acceleration due to gravity, little g, the same value experienced on planet Earth, is being simulated in this space station in outer space. So this is a really cool classic problem. All right, in question 22, answer the following questions using both qualitative and quantitative reasoning. So we're asked basically, can an object move in a circle without having centripetal acceleration? Can it move in a circle without having tangential acceleration? So we're going to talk about the 3 types of acceleration. First and foremost, let's look at each of these 3. So on the left side here, we have centripetal acceleration. Okay, that's equal to tangential velocity squared divided by radius. Next, we have the angular acceleration. Angular acceleration is equal to a change in angular velocity over change in time. Then we have our tangential acceleration for an object moving in a circle, and that is the change in the tangential velocity over a change in time. Okay, so you may recall that omega multiplied by r is equal to the translational quantity of velocity. So if we were to sub in omega r into here over t, we would find that omega over t, or the change in angular velocity over change in time, well, that's going to be equal to the angular acceleration. Therefore, the angular acceleration multiplied by the radius is another way to express the tangential acceleration. I want you to keep that in mind as we move forward here. All right, so let's talk about these quantities. The centripetal acceleration is always inward, right? That's the direction of the centripetal acceleration. The tangential acceleration is at a tangent, okay? And it applies to an object at a given radius, or a point at a given radius, all right? Centripetal acceleration applies to an object at a given radius being manipulated into a circular path. Angular acceleration is different, though. Angular acceleration has a direction, in this case, that's coming basically up and out of the page, okay? So it's very different. And it applies to an entire rigid object that is in rotation, regardless of the radius. All right, so I wanted to provide a little intuition for all 3 of these before we move forward. So 1 points inward, 1 is always at a tangent to the circle, and the angular quantity in this case is up and out of the page. And if it were rotating clockwise, it would be down. All right. So let's put some numbers in here and answer this problem. First and foremost, an object must have centripetal acceleration because the direction is constantly changing. So we may not be concerned with the magnitude, but because the direction and because velocity is a vector quantity with both magnitude and direction. Even with a constant magnitude, an object in a circular path must have centripetal acceleration for the simple fact that its vector is constantly changing. Okay, so let's now look at some of these other accelerations. Let's look at tangential acceleration. Now, I mentioned previously that tangential acceleration is equal to the angular acceleration multiplied by the radius, and I'm showing that here again for you to see. So, if omega is constant, in other words, if we have a constant angular velocity, then change in omega over change in time is 0. If omega and acceleration, if the angular acceleration is 0, then we're saying 0 multiplied by r equals 0. So yes, it is very possible in this case here for an object to be in circular motion and not be accelerating tangentially. That object is simply moving at a constant angular velocity. Okay? And so we're showing here mathematically, just by putting in 0, so using some quantitative reasoning here, that if the angular acceleration is 0 because the angular velocity is not changing, then we get an answer of 0. Okay, all right, so question 23, we have some children on a carousel. It is initially at rest. As always, I'm going to go ahead and underline that. We're given the angular acceleration, we're given the fact that it accelerates angularly to 0.4 radians per second. We're given the time for this acceleration, and we're asked, what is the angular acceleration, or alpha? What is the linear acceleration? And of course, as we just went through in detail in the last question, if we're talking about a linear quantity and a tangential acceleration, we're referring to a specific place or object at a given radius from the axis of rotation. Of course, any object at the axis of rotation where r equals 0 will not experience an acceleration. But in this case here, the objects are 3 meters from the axis of rotation. Okay, let's look at this one. Omega naught. I underline that. It's 0, so we start at rest. Omega final. We accelerate to 0.4 radians per second. We are given the time, which means we can say the angular acceleration is equal to omega final minus omega naught over delta t, or change in time. We have all the quantities to put these in and solve for the angular acceleration to be 0.04 radians per second. All right. The next question is, what about the linear acceleration? Well, in the last problem, we talked at length about the 3 types of acceleration that could be occurring for an object in a circular path, all right, or an object rotating. So here, the tangential acceleration is equal to the angular acceleration multiplied by the radius. We have everything we need to solve this. We found the angular acceleration in part 1. We're given the radius or the distance from the axis of rotation, so we can simply multiply this out. Now you might say, what happened to radians? Radians is a placeholder. We drop the radians, we pick up meters to get base SI units for linear or translational acceleration. Question 24, Sophia is on a unicycle. The wheel begins at rest. Let me underline that. It accelerates uniformly. Let me underline that. Let me underline the fact that it is counterclockwise, because that is important as well. Remember these angular quantities. So this would be basically coming up as I'm oriented up using the right-hand rule. okay? And depending, it would be going into the computer screen. All right, so let's see. The direction, the angular velocity is 15 revolutions per minute. In a time of 6 seconds, find the angular acceleration. So we're given revolutions per minute. Okay, so let's write down what we know, and let's go ahead and get our angular quantity figured out here. So we're given 15 revolutions. There are 2 pi radians in 1 revolution. There are 60 seconds in 1 minute. All right. And that gives us radians per second. That's the correct units for angular velocity. So we get an answer of 1.57 radians per second for Sophia's final angular velocity. All right, great. So find the angular acceleration of the wheel. So the angular acceleration is equal to the final angular velocity minus the initial angular velocity divided by the change in time. Because the wheel begins at rest, we can call omega naught 0, which means we can plug and chug and get an answer of 0.26 radians per second for the angular acceleration of the wheel. In question 25, we have a car that is traveling at 23 meters per second around a flat curve, so we don't need to resolve force normal. There's no banking going on here, with a radius of curvature of 100 meters. The car is going as fast as it can without skidding. What is the minimum coefficient of friction that is necessary for the car to move around the curve without skidding? In other words, to stay in circular motion. Let's write down what we know. We know the radius of curvature, we have the velocity, and we're asked to find mu. So we really don't know a lot. And many students have come up to me about this problem and said, you forgot some information in here. No, you have everything you need to solve this problem. Let's do what we always do. Let's sum the forces. Let's sum the inward forces, and let's sum the vertical forces, even if we don't think it's going to help us, because it will. All right. So centripetally, we have the force of static friction, and that is equal to the tangential velocity squared divided by radius, that quantity multiplied by the mass, which we don't have. Let's move on vertically. We have force normal minus the force of gravity is equal to mass times the acceleration vertically. However, the object is not accelerating vertically. Therefore, we know force normal is equal in magnitude, opposite in direction to the force of gravity. That's something that we've seen over and over again, and it has proved to be very important in this course. All right. Physics is fun. Anytime you're asked about coefficient of friction, I said you might want to write down that the force of friction is equal to mu multiplied by mass times gravity, or in this case, force normal. So because we know force normal is equal in magnitude to mass multiplied by the acceleration due to gravity, we can take that and plug it in here, which we've done a number of times throughout this course. And that tells us that the force of friction is equal to mu times mass times the acceleration due to gravity. Now, let's look at putting that and setting it equal to our mass times the centripetal acceleration. Well, what do you notice here? You can see that we are able to cancel out mass. So you didn't need mass. Mass did not matter. So in this case here, mass cancels out, and we had everything we needed to solve this problem. We can now rearrange this equation, dividing both sides by the acceleration due to gravity, little g. We can solve for mu to be equal to 0.53. Question 26. A carpenter cuts a piece of wood with a circular saw. The saw accelerates, let me underline from rest, with an angular acceleration of 14 radians per second to a max speed of 15,000 revolutions per minute. So let's look at what we know. We know our maximum angular velocity, and we're also given the angular acceleration here. Part 1, what is the maximum speed in radians per second? All right, let's do a little dimensional analysis to convert revolutions per minute to radians per second, which would be our base SI units here for omega. And we have revolution. In 1 revolution, there are 2 pi radians. In 1 minute, there are 60 seconds. That gives us radians per second. Plug and chug, 1,571 radians per second. Part 2, how long does it take to reach this maximum speed? All right. Well, let's use one of our UCM, uniformly circular motion equations, the angular rotational analog to what we learned in our first unit of this course, which dealt with translational kinematics. So we have the omega final equals omega naught plus alpha times time. All right, so we can use this one because omega naught is 0. And there, as we've talked about throughout the course, there's other ways you could have solved this problem. So we have the final angular velocity, which we found in radians per second. We have to have it in radians per second. That's base SI units for angular velocity. And we can say that is equal to 0 because it starts at rest, plus the angular acceleration given to us in the problem. And so now we just divide both sides by the angular acceleration. We find the time is equal to 112 seconds. Part 3, how many complete revolutions does the saw make while reaching this maximum speed? Well, so we're going to need to do another conversion here. All right. And we are given the omega naught, which is 0. We have the time, which is 112 seconds. We have the angular acceleration. So we can say that the change in theta, which is in radians, is equal to 1/2, 14 radians per second, multiplied by the time squared. But we're asked how many complete revolutions. All right, so we need to do a conversion, as I already alluded to. We get our radians, 87,808 radians. Okay, so let's convert radians into revolutions. And we know how to do that because we know there are 2 pi radians in 1 revolution. Again, you're dividing by this quantity, 2 pi, and you should get just a little under 14,000 revolutions for part 3 of question 26. All right, so question 27, we have a derivation here. We have an amusement park ride. We're given a radius of x. It's spinning at a length L, and it's spinning with a maximum angular speed. All right, we have a cable. It's at an angle theta. We are asked to derive an expression for the maximum angular speed, omega, of the rider in terms of these quantities, little g, theta, x, and L. All right, so we've been practicing derivations throughout this course, and I don't want you to ever be intimidated by them. Just follow the 3-step plan. Step 1, get a layout of the situation, get an intuition, think about what is happening in the problem, draw some sketches, and just kind of overall reason through what is happening. So let me model that now. So we're given a diagram, and we have an object being manipulated into a circular path by a center-seeking force. So we're going to be looking at the centripetal forces involved here. We're also asked to derive something in terms of an angular quantity, but all of our quantities we have initially are translational. So we're going to need to, at some point, convert from translational to angular quantities. We have an angle of inclination from the vertical, which means let's analyze our right triangle here. We have a force of tension in the x. Wait a minute, that's our inward force. Okay, and then we have a force of tension vertically, which we're going to end up realizing is equal in magnitude to the mass times acceleration due to gravity, which we've seen many times before. Step 2, sum the forces. Let's sum the forces inward. So if we look at that, we can acknowledge or see that the force of tension in the x, or inward direction, is equal to mass times centripetal acceleration. Now, looking at our geometry, the force of tension in the x, which is our inward, as I've said repeatedly, is opposite of angle theta, and the hypotenuse of our triangle is the overall force of tension, capital T. So we can say that the overall tension, capital T, multiplied by sine theta is equal to this component. We can then substitute that in and say T sine theta equals mass times the centripetal acceleration. Let's look at the vertical components. So vertically, we have the force of tension vertical component, which is the adjacent side of our right triangle, which means capital T force of tension cosine theta is equal to the vertical component of the force of tension. And we can say that minus, if we call it positive down negative, that minus mass times the acceleration due to gravity is equal to mass times the vertical acceleration. However, the object is not accelerating vertically. Therefore, we can say these are equal. If we set these equal to one another, we can then stop and look at our two equations. We have two equations, ostensibly not quite sure where to go with this, so we're always going to attempt rearranging one in terms of the other and substituting that quantity in. Well, we can isolate the force of tension by dividing both sides by the cosine of theta in our vertical summation. Then we get the fact that the force of tension is equal to mass times the acceleration due to gravity divided by cosine theta. We can now say, since they're equal, let's substitute that into our inward summation, and we get this quantity here. So we have this expression. Now we're getting somewhere. I'm going to go ahead and put sine theta over 1. So you can say, oh, sine theta divided by cosine theta, that's tangent theta. So we can simplify this even further and set that equal to mass times the centripetal acceleration. Wait a minute, let's divide both sides by mass. Mass doesn't matter in this case, which means we can simplify this even further. So if we get the little g multiplied by tangent theta, we can set that equal to the centripetal acceleration, which is given in terms of the tangential velocity, which is a translational quantity. It's time to go ahead and convert this translational quantity into a rotational or angular quantity. Recall that the angular quantities are equal to the linear quantities divided by the radius. So we can multiply both sides by radius, and we can say that the tangential velocity is equal to omega multiplied by the radius. So we can make this substitution now. Let's go ahead and do so. And remember, it is squared. So we can plug it in and square it. All right. So we get some simplification here that we can do with our radius. We get one radius in the denominator, and we have radius in the numerator squared, which means that we can divide or cancel one of those out. Then we can go ahead and divide both sides by the remaining radius to cancel these guys out completely. And we finally can say that the angular maximum speed is equal to little g times tangent theta divided by the radius, and the square root of that entire quantity is going to be equal to this. Again, what we did here is we just simplified with the radius, canceled this one out here, and then divided both sides by the radius here to end up getting this expression. Okay? All right. So the last step is going to be, we need to get this in terms of x and L. Well, we know the overall radius, this overall distance. So this blue line here is the radius. We know that it is composed of two segments, x and this piece here, which is this horizontal component. We can find this quantity by taking L and multiplying it by sine theta. So remember, this is L, and we want this adjacent length, all right? And to find that, we can use trig. It is opposite, all right, of angle theta. And so L, or the hypotenuse multiplied by sine theta, plus x will give us the total distance, which is r, the radius from the center of rotation. So we can take that mess and substitute that into our denominator to get our final answer, that the maximum angular speed is equal to this whole quantity here. All right. Good practice deriving an expression. Question 28. What is the magnitude of the gravitational force of attraction between two asteroids in space, each with a mass of 50,000 kilograms, and we're given the distance that separates them from their center of mass? So these final problems on this unit, we're using the universal law of gravitation, and we're also going to be looking at universal gravitational potential energy. Let's look at this problem here. So we're going to use the fact that we know the expression for the force of gravity is being equal to, and this is Newton's universal law of gravitation, equal to our constant big G multiplied by our two masses, because we have two objects, all right, in this, to calculate the force of gravity. We need and must have two objects, divided by the radius squared. Okay, so this is on your College Board equation sheet in this form. And so this first problem is nothing more than a plug and chug. Let's look at the problem and recall that r, which is in our denominator, and squared is going to be the distance between the center of mass of the two objects, in this case 3,800 meters. So we have a classic inverse squared relationship here that we're going to get into in some of these upcoming problems. And you've already heard me bringing up Coulomb's law and making that comparison, as Coulomb's law is also an inverse squared relationship. But we'll get to that in the upcoming problems. So we solve for the magnitude of the gravitational force, and here's our answer. Plug and chug, let's move on. I also like to always show you in some of these first problems how units, I've implored you throughout the course to show not being asked. The units for a big G here, I'm showing all of these units canceling out and simplifying to this here, mass times acceleration essentially, which is force or newtons. Question 29. Given the radius of the Earth is 6.37 times 10 to the 6 meters. Determine the mass of the Earth. All right, so we have our equation for the universal law of gravitation. We have, I'm going to go ahead and mark that out here. I want to talk about it. So we know the force of gravity. Force of gravity for an object near or on the surface of Earth is going to be equal to the mass of that object multiplied by the acceleration due to gravity, or little g. Okay, so if we are to find the mass of the Earth, let's move forward and simplify this a bit. We can say that the acceleration due to gravity is equal to big G multiplied by the mass of the Earth divided by the radius squared. So you might say, what happened to mass 1? Well, right here is what happened. So it canceled out, okay? Mass 1 could be, say, the mass of me on planet Earth. It cancels out. And so we're left with little g equals big G times the mass of Earth divided by the radius squared. Well, we know little g. That's the gravitational field strength on planet Earth. So we know that's equal to 10 meters per second, or 10 newtons per kilogram. So we can put that in, and now we can solve. So we know little g, we plug it in, we know big G, which is a constant, and now, since we're given the radius of Earth, we can solve this and find that the mass of Earth is equal to 6.1 times 10 to the 24th kilograms. Again, in this problem, as we will in several others, we're using the fact that we know little g on planet Earth. We know it is equal to 10 meters per second, and given other quantities, we're able to solve for, in this case, the mass of the Earth. In question 30, the moon orbits the Earth in a circular path at a constant speed. If mass capital M is the mass of the Earth, little m is the mass of the moon, r is the distance between their center of mass, whereas to derive an expression for the moon's orbital speed in terms of these quantities. Okay, let's think about what's happening here. We have an object, the moon, being manipulated into a circular path by a center-seeking force, and that force must be the force of gravity between those objects. So in this problem, the first of many, we're going to say, okay, force of gravity is equal to mass times tangential velocity squared divided by r, or the centripetal acceleration. Then we're going to use the universal law of gravitation for the force of gravity, and we're going to set that equal to mass times the centripetal acceleration. Okay, so this is the first of many times we're going to do this. And if you look here, the mass of the smaller object, in this case, the mass of the moon, which is the object being manipulated into a circular path, cancels out. So the mass of the object that is orbiting the Earth, i.e. the moon, doesn't matter. It cancels out. So moving on to look at this, we can then say, okay, what about the radius here from our tangential acceleration? So we can multiply both sides by radius. We can then rearrange this for the velocity, which is the tangential velocity, or magnitude of the speed in this case that we're being asked to find, is equal to big G multiplied by the mass, capital M, which is the mass of the Earth, divided by r, that quantity, square root. And that's going to give us the orbital speed. Again, take-home message here. The mass of the object orbiting doesn't matter, It cancels out mathematically. We've seen this throughout the unit. Please remember that. Here we're showing it mathematically. Question 31. A dwarf planet has 1/200th the mass and 1/5 the radius of the Earth. Okay, we're comparing some other planet to Earth, and we know some things about planet Earth. What is the value for little g on the surface of the planet? Okay, so we're being asked about the value of little g, which in class I've said meters per second, acceleration due to gravity, also the gravitational field, which is expressed as kilograms, or excuse me, newtons per kilogram. That's the gravitational field strength. Newtons divided by kilogram. So we're asked about an object essentially close or on the surface of this dwarf planet. Let's look at what this would be like. We have the force of gravity. That is equal to the universal law of gravitation. We have that expression. Then we're saying the force of gravity for an object on or near the surface of this dwarf planet is equal to the mass of that object on or near the surface of this dwarf planet multiplied by the gravitational field or the acceleration due to gravity, and that is equal to the universal law of gravitation. Then we're going to look at what this is here. Mass 1, cancel, cancel. All right. So mass 1 being the mass of the dwarf planet. Okay. So that is incorrect. Mass 1 is not the mass of the dwarf planet. Mass 1 is the mass of the object that is on or near the surface of the dwarf planet. Mass 2 equals the dwarf. My fault. Okay, so mass 2 is the dwarf planet. Mass 1 is the object, whatever that might be, that is on or near the surface. And it is that mass that will cancel out. So I apologize about that mistake here. Let's go ahead and simplify this now. We get little g, we get our simplified expression, and what do we know about little g on planet Earth? Well, we know College Board says we can call it 10 meters per second, so that's what we're going to do to simplify our calculations here. So we're being asked to find and compare this quantity, little g, to that of Earth. All right, so this is sort of the mathematical quantitative piece that I wanted to lay out first and foremost. Now, let's get to what we're going to do here. We're going to basically acknowledge the fact that the constant big G was used to calculate the acceleration due to gravity or gravitational field on planet Earth, which we've already substituted in. We're going to be using that for the dwarf planet. So we're going to essentially ignore it. We're comparing the new radius and the new mass of this dwarf planet to the value 10. That's all we're doing here mathematically. So if we look at 10 meters per second, and now we say the mass is 1/200th. Okay, mass is directly proportional to little g in this case. So this dwarf planet is 1/200th. So it is very, very small compared to Earth. So we would expect that that would lead to a smaller value for little g. In fact, 1/200th of 10. So we're going to take 10 and divide it by 200. Then once we get that quantity, we're going to analyze the radius. What do we know about radius? We know that it is in the denominator and it is squared. We know that little g is inversely proportional to the radius and the square of the radius, in fact. And so if this is 1/5 the radius, it's much, much smaller. Well, as radius goes down, little g value goes up. In fact, even more so because it is squared. This is an inverse squared relationship, just like we've talked about in the past with Coulomb's law. So we're going to put our value in for the new radius of the dwarf planet of 1/5, which means if we looked at this, it's going to be 25 times greater. All right, so multiply both sides by the inverse of 1/5 squared. That is equal to 25. So what did we do here? I went through a lengthy process here to show you something that is always going to be true for an object on or near the surface of any planet. The mass of that object will cancel out, and you'll end with this here if you're solving for the acceleration due to gravity or the gravitational field on any planet. You're going to end with this. Then we acknowledge that we knew what it was on Earth. We know it's 10. Then I went through why I'm essentially ignoring big G. Then we did the following. We said it's directly proportional to the mass. So if the mass was decreased by 200 times, then I need to decrease 10 200 times or divide by 200. Then we said the radius went down. If the radius goes down, little g goes up. And the radius is squared. So little g goes way up. In order to do that, we took our value 1/5 squared. And then we took the reciprocal of that value. And I think the biggest thing for these problems, which you will see on the AP exam and you will see on my exam, is that just think about what's happening before. The value goes down for mass. That means the value for the gravitational field goes down. The value for radius goes down. That means the value for the gravitational field goes up. And don't forget, radius is squared, so it goes way up. In this case, 25 times greater. So 10 divided by 200 multiplied by 25 gives us a gravitational field of 1.25 newtons per kilogram, or meters per second per second. All right, there we go. Question 32. At the surface of the Earth, an object of mass m has a weight of w. What is weight? Mass times the acceleration due to gravity. If this object is transported to an altitude that is twice the radius of the Earth, twice the radius of the Earth, what can be said about m, or the mass, and w, or the weight? All right, so planet Earth, and we're looking at the fact that we have an object that was initially on the surface, and that's where we have its weight, was on the surface, where the weight is equal to mass times the acceleration due to gravity. And so I'm showing here, this is a classic, so get ready, all right, that we have the radius of the Earth, and we're told that it is at an altitude of twice. So we need to take the radius and add this altitude. So we're going to end up with not 2r, but 3r being the distance between the center of mass of the object and the center of mass of the Earth. All right, so let's make some comparisons here. Force of gravity on or near the surface equals mass times the acceleration due to gravity on or near the surface, which is by definition the weight. And that can be found for an object on or near the surface of the Earth by setting that equal to the universal law of gravitation that states force of gravity is equal to big G, the constant, multiplied by, in the numerator, mass 1, mass 2, and that divided by the distance between those objects squared. We know that we are given the relative, distance as 2 times r. We went through the fact that we need to add the altitude 2r to 1r. That gives us 3r. Now let's look at what happens. We just went through this, and it is absolutely critical because this comes up over and over again on the AP exam. All right, so we have an inverse squared relationship here. We have an inverse squared relationship, and so we are showing that, I'm so used to writing omega, that weight is not equal to, weight is proportional to 1 over r squared. So it's inversely proportional to the distance squared. And we are now looking at an object that has a value here of 3 times greater. So if we put that value in and we square it, we're saying that the value there is 9. What does that mean? Well, inverse squared relationship. So the objects are further apart. That means that the force of gravity or weight's going to go down. And it's not going to go down 3 times. It's going to go down 3 squared or 9 times. It's going to decrease by a factor of 9. So our answer here is weight divided by 9. It's 1/9 the weight. And the next part of this, what can be said about m, or mass of the object? Mass is a property. It's the amount of matter in a substance. That's not going to change. Mass stays the same. Question 33. Find the magnitude of acceleration due to gravity of an object on Earth given the mass of the Earth and the radius of the Earth, and big G. This is one of those where you're going to kind of prove to yourself, what should we get? Well, we should get about 9.81 meters per second, or 9.81 newtons per kilogram. Let's see what happens. Let's prove it to ourselves in part A here. All right, so we have force of gravity, which for an object on or near the surface of the Earth is equal to mass times the acceleration due to gravity. That is equal to the universal law of gravitation, because that equals force of gravity. So we see once again that we're going to have the mass of the object is going to cancel out. All right. And next, we're going to simplify this and plug in our values, and lo and behold, we get 9.81 meters per second, or 9.81 newtons per kilogram would be the gravitational field. All right, so we've shown that. In part B, it says, what about a space station that is 400 kilometers above the Earth? So we're going to need the radius of the Earth plus the altitude. We looked at that in the derivation in question 32. All right, so we're going to be adding 400 kilometers to the radius of the Earth, and we're going to go ahead and solve for the acceleration due to gravity for this object, this space station. And you can see here, we have the object on the surface of the Earth here, and then we have the radius of the Earth, but we're going to be adding 400 kilometers. All right, that should be kilometers right there, not meters. We're adding 400 kilometers to that value, so we're out here a little bit. Let's go ahead and see what happens. We make a prediction. The value for little g should go down. Why? Because the distance between the center of mass of the Earth and the space station is greater. So we're going to see a value that is less than 9.81. Indeed, we get 8.7 meters per second. And lastly, how fast does the space station need to move to stay in orbit? All right, so this means we have an object being manipulated into a circle, into a circular path by a center-seeking force. The center-seeking force must be the force of gravity. And so we know we can set the force of gravity equal to the mass times the centripetal acceleration. ultimately rearranging to solve for the orbital speed. So here's what it looks like. We're going to rearrange this, and we get that the velocity is equal to the square root of our constant, big G, mass of the Earth, which is, remember, we've shown now in several problems, this is going to cancel out. Mass 1 times G is equal to force of gravity. Mass 1 goes away. So and really in our in this example here, it's canceling out with the mass from the centripetal acceleration and centripetal force, mass times the centripetal acceleration. And whether it is a pig or a satellite or a dwarf planet or a moon, the mass of the orbiting object cancels out and doesn't matter. And we're left with the only mass being the mass of Earth in this case here. So let's plug in values and find our final answer to be equal to 7,669 meters per second. 7,000. Wow, that thing's really moving fast. Question 34. We have a 2-kilogram object. We have its weight on Earth. If the acceleration due to gravity on Mars is only 3.71 meters per second compared to that on Earth, what is the object's mass and weight on Mars? Okay, so let's look at this. What is weight? Well, for an object on or near the surface of a planet, it's mass times the acceleration due to gravity. And we have everything we need. We have the object's mass, we have the acceleration due to gravity. So we can solve and say it's 7.42 kilograms times meters per second squared, which is the base SI units for the derived unit of a Newton. Okay, what about the object's mass? Mass is a property of the object. It's the amount of matter in the object, and that's not going to change. All right, question 35 here. We are going to start getting into some discussion of the universal gravitational potential energy. And in class, I have explained this. I'll explain it again in case it didn't quite make sense, but we're going to need this intuition on this problem, and College Board will always have 1 or 2 of these on their AP exam. So this is very important here. In or on the problem set, I've shown how we end up with the fact that r in the denominator is no longer squared. That is very, very, very important here. It is not squared. And we talked about change in kinetic energy, changes in mechanical energy being equal to work, being equal to force times a distance, that force exerted. In this case, our distance is r. And if we set that equal to, or not set it equal to, but if we take our force and plug in the universal law of gravitation, that shows where this will cancel with one of these guys squared down in here. Okay, so that's quick and dirty there. I've done this in class. I'll do it again. Quick and dirty. So the key point, r is not squared. Another key point, the value for this is always negative. And in class, I talked about the fact that we are setting our zero line for the universal gravitational potential energy at a distance infinity. So at an infinite distance, that is our zero line. And because of that, as we get closer and closer and closer, we become more and more negative. As we get further and further and further away, our value for the universal gravitational potential energy becomes less negative. So more negative as we get closer, less negative as we get further away, and at infinity, 0. Okay, so that is why the value for the universal gravitational potential energy is negative. Furthermore, the r in the denominator is not squared, and that is due to the fact that we are looking at these energies, and we're also talking, we can look at the amount of work that these energies are doing, and work is equal to a change in kinetic energy, and I can show you all this again in class. Let's get to question 35 here. A satellite is orbiting Earth at a circular path of r and a kinetic energy k. If the satellite is moved and enters a new circular orbit, that is 2r. Derive an expression for its new kinetic energy. Well, let's look at what this is. Our total mechanical energy is equal to the kinetic energy minus the gravitational potential energy. All right? So we can say kinetic energy is equal to the universal gravitational potential energy. 1/2 mv squared is our value for kinetic energy, which we're just going to call K, and we can set that equal to the positive value of gravitational potential energy. And now we're going to analyze it from a mathematical standpoint. So kinetic energy is equal to big G, mass 1, mass 2. More importantly, guys, all we're looking at here is this comparison. That's it. That's all we care about. We want to look at what we had here, and now what do we have at our new circular orbit? Well, we have a radius that is 2 times greater. What do we know? We know kinetic energy is proportional to 1 over r. As r goes up, kinetic energy goes down, and it is not a squared inverse relationship. It's just simply an inverse relationship. So if the radius goes up 2 times, then we're going to see the kinetic energy is going to go down 2 times. It's that easy. All right. Now, the key is distinguishing in the future. Are you looking at the universal law of gravitation? Are you looking at the force, in which case the radius or the distance between the center of mass of 2 objects is squared and in the denominator? Or are you looking at the universal gravitational potential energy, in which case the distance is in the denominator, but it is not squared? So it is an inverse proportional relationship. If one goes up 2 times, the other goes down 2 times. That's simple. Question 36, a binary star is a phenomenon in which 2 stars are orbiting around their mutual center of mass. Cool stuff. If the mass of the primary star is 4m and the mass of the secondary is m, what is the gravitational potential energy of the 2 star system if they're separated by a distance r? So, gravitational potential energy, capital U sub G. In this case here, we know it's negative. We know the radius is in the denominator, but it is not squared. And we're just putting in our values, m and 4m. That's all. So our derived expression is negative 4 times big G times masses squared divided by the radius. That is the gravitational potential energy between these 2 stars. Question 37. College Board will always ask you to be able to distinguish between the inertial mass and gravitational mass, and to be able to come up with experiments to test both of those, and to show that the values for gravitational mass and inertial mass are the same. In this case here, we have objects A and B. Design an experiment that would determine which object, A or B, has the largest gravitational mass, given that they have the same gravitational field. All right. Next, describe an experiment to show A and B, which would have the largest inertial mass, regardless of the gravitational field. All right, so let's get to it. Experiments. We have on the left the gravitational. Well, that's the weight. So really, any way that you're balancing objects, like on a triple beam balance or whatever, you can show that you can calculate the gravitational mass by saying the force of gravity at a constant gravitational field is equal to the mass multiplied by that gravitational field strength, or little g. The inertial mass, you need a way to find and measure acceleration. So the inertial mass on any exam or any problems, you need to simply find a way to be able to have both the force and the acceleration. All right. So in class, I was like, all right, I'm on a skateboard or whatever, and we're going to neglect non-conservative forces and friction, and I'm going to exert a force, and you're going to measure my acceleration as a result of that force I just exerted. And by doing so, we can say that mass is equal to the force that was exerted and the acceleration that resulted from that force. And that will give me my inertial mass, which will be the same as my mass calculated from the gravitational field and the force of gravity. So there are any number of ways that you can design experiments, but for inertial mass, you need to be able to have a way of calculating force, and you need to find that acceleration, so you can divide force by acceleration to get the inertial mass. For the gravitational mass, you need a way to basically compare two objects, like on a balance, given a same constant gravitational field strength. So that concludes the Unit 5 problem set solutions, and I will see you guys in class.